Hello everyone. Today I'm going to continue with ACI Part 2, which is a continuation from ACI Part 1 on our CPOC YouTube channel. We're now going to dive down a bit deeper and give a lower level overview of ACI, etc, etc. So the structure of this presentation, Part 1, I'm going to talk about the ACI components. So these are the new names, terminologies and attributes, what they are, what their purpose is, how they relate to one another, and how they work in the overall ACI fabric solution. Then the second part of this video, we're going to talk about the ACI fabric. So that's more, how does the spine connect to the leaf? What is the routing? It's layer 3. What routing protocols? How does everything work from that point of view? So first, talking about the components. First thing we really need to talk about. You saw the spine and the spines and the leaves in the previous diagram. This is the hearts and brains of it. This is what's known as the Application Policy Infrastructure Controller, or the APIC. So this is GUI based, and this is actually where you provision your network. This is where you actually manage everything focused around ACI. Now the cool thing about this, it's very scalable, and it's got redundancy within it. Not only that, but it's actually got an API, open source API, which is XML based, which means you don't necessarily have to just run the Cisco GUI to manage the ACI fabric. You could develop your own third-party tools that could do this, and you could run programs like OpenStack. You could even use Cisco UCS Director, all these kind of tools that can help orchestrate everything, because we want to manage the network, we want to automate as much as possible, we want to sort of automatically provision things, so it's all about less and less manual intervention. So we could kind of integrate the whole ACI fabric with some storage, with a vCenter, and set up the orchestration that's events based, tie everything in together how it needs to be tied together, which really improves management, scalability, etc, etc. And you can create your own in-house app, whatever you want to do to manage this as well. So this is the fabric. You saw a previous diagram of this, of the spines and the leaves. Just a reminder that you can't connect a leaf to another leaf. Likewise, you can't connect a spine to another spine. It won't allow you. This is the only way it can work. You can only connect a spine to a leaf and vice versa in this kind of method, as you can see on the diagram. So I discussed the APICs in the previous slide. You actually have to have a minimum of 3 to form a cluster. Otherwise it won't work. You need to have some sort of redundancy to fall back on. So what happens is, when a cluster is formed, all data is synchronized between all APICs. So if an APIC made an update to a local leaf here, in a very short space of time, the other APICs will know about it as well. They'll have the same perspective of the overall fabric. This is really cool in the sense that obviously if one goes down, the rest will have the replicated data. So the data is replicated in what's known as shards. So it's the actual data being synchronized across all APICs, which is pretty cool. How is an APIC connected? Well, there's 2 main types of connections. There's the out-of-band management connection, so we can access it in the first place. And then there's the connection from the APIC to the leaves themselves. So obviously the APIC needs to be connected to the leaf to discover it. In fact, when you first turn on an APIC and you're first starting with the fabric, it discovers the primary APIC. One of these APICs will be a primary APIC, and you decide that when you first boot it up. Also to mention that APIC is a UCS C220M3 server. That is pretty much what it is. It's all pre-installed and everything, so you just pretty much turn it on, give it an IP address to manage, provide a network for all of this, and then it will self-configure itself once that's done. That's the whole idea of it, network provisioning, so that there's less manual intervention, etc., as explained in the previous slide. So how can you connect it to the leaf? So you can have it as one single link, not recommended. Here is just a simple port channel to the same leaf. Then what you can also do is have the APIC actually act as a VPC client to leaves. So what is a real cool feature with an ACI is actually two leaves, although you can't connect a leaf to a leaf, as you know, can actually form a VPC pair without a peer link or a peer keep alive link. What it actually does, it runs enhanced Cisco Fabric services between the leaves via the spine. As you don't need a peer link or a peer keep alive link in this instance, it actually eliminates a lot of the caveats, which if some of you have worked with VPC, you'll know exactly what I'm talking about. These caveats are gone now, and it provides the functionality where you could connect an APIC, and it doesn't have to be an APIC, it can be a switch or whatever it is, whatever you need to connect downstream to a leaf, to the leaves themselves as a VPC client. So leading on now to that, what can you connect to the leaves as well as the APICs? You can connect FEXs, and then you can dual home a server to FEX, just like that. You can also just simply attach a server. Also, naturally in your environment, you will no doubt have existing firewalls, load balancers, application acceleration devices, etc., that you're going to want to include as part of the fabric. So these are your layer 4 to 7 services like that, so which you can directly attach as well. You can connect a router or another switch. You could even connect two switches downstream to the upstream leaves, and that would be a back-to-back VPC, so you could have one overall logical port channel for that. And the connections can either be 1 gig or 10 gig. So going back to what I was saying just now, when you first turn on the APIC and it forms a cluster with the other APICs, it will first discover, you ask it to discover the leaf that it connects to. So in this case it will discover this leaf where my mouse is at the moment. Then the leaf will be connected to a spine or a few, and so it will then discover the spine, then the spine will discover another leaf, and so on and so on and so on and so on, until the whole network is seen end to end and knows about each other. Configuration will not allow a spine to be connected to a spine, as I said, or a leaf to a leaf. So once everything is connected end to end, it will automatically provision itself with its own network. All you have to do when you first power on the APIC is choose the subnet. It will do everything else for you. It's at a point where you don't need to know as much as you used to about it all. It's all, like I said in the previous video, it's all about the application, providing a network for the application, and then applying the cause policies, applying the firewall rules, etc., on the APIC itself, then pushing it down to the network, only between the areas where it required those types of things, ports open or closed. So, these are the terminologies. Now imagine you were a provider hosting multi-tenancy. If you're hosting multi-tenancy, you'll need two different tenants, so it's just different companies you're providing this for. So that's simply what a tenant is. It's a logical separator for each customer. Doesn't necessarily have to be a customer. It could be a business function within a company. However you want to do it, the flexibility and granularity is important here, and we need to sort of tweak it to make it as granular as possible. This is kind of hierarchical. Then there'll be, let's just pretend the tenant is for a customer in this sense, and then it will kind of make more sense for these below attributes here. Then you've got a private network, so that's simply the equivalent of a VRF. As you know, any customer could potentially have multiple VRFs for various purposes. So once again, it's just the ability to hierarchically, logically separate. Then you got the bridge domain. So this could be just one subnet or multiple subnets. Might want to be multiple subnets, because if you want to treat those multiple subnets in the same way, that's where you put them in the bridge domain. Then at the bottom we've got the endpoint group. So this is pretty much the container for objects that require the same policy. What I mean by that is the following. Remember we looked at the web, the app and the DB model in the previous video. Well, you may want to have all your users on laptops to be in a certain VLAN. So for the endpoint group for users, you would actually apply VLAN 10. I'll probably use VLAN 10 quite a bit, as when I say VLAN 10, this is just the example for that EPG for users. Then you could have another endpoint group for all the cluster of web. You may require a huge cluster of web servers. So you put them in another endpoint group, and you put them in a different VLAN, and then you associate that different VLAN, say for example VLAN 20, with the endpoint group for web servers. It's all about the manageability. It's all about the ease of provisioning, especially for many multiple members that are kind of part of the same thing. So you could have tens of web servers in a cluster. If you're a huge database company, you could have many databases that, from a certain ways, from at least a networking perspective, you could treat the same way, so you don't have to go around each one manually. This is what this is all about. Really powerful. This is diagramming what the previous slide said. So in our fabric we've got two tenants, tenant A and tenant B. And tenant A happened to have two VRFs. Tenant B only got one. Within the VRF, standard routing, you could have multiple subnets within a VRF, or SVIs. We think of it from a VLAN point of view. It's got a bridge domain here with one subnet, bridge domain, two subnets. Obviously the guy who set this up wanted subnet B to be treated in the same way as subnet C. I mentioned endpoint groups. I mentioned that VLAN 10 would be the VLAN for clients, as an example, and VLAN 20 perhaps would be the VLAN for the web servers. How else can you classify endpoint groups? Well, another way of doing it is VXLAN. We could do it by NVGRE, which is Microsoft's equivalent implementation of that. As you know, VXLAN is very scalable. It can now cater for 16 million different types of VXLAN IDs, compared with the 4,000 plus for VLANs. You can categorize on subnets as well. So how else will customers want to categorize things? So this is what's in the future. Categorizing via VM attribute. Categorizing via DHCP pool, or even DNS, or anything the customer wants that's realistic to be able to categorize as an endpoint group. This is once again talking about the EPG. So I'd mentioned you could use VLAN 10 or subnet X or subnet Y, put it in an EPG. You could have multiple VLANs if you want to treat in an EPG, if you want to treat them the same way. I mentioned this at the very end of slide 1, the application network profile. The equivalent of the service profile in UCS is the application network profile in ACI. So what the actual application network profile is, it includes all the EPGs, so EPG-A, EPG-B, and EPG-C, and the relationship between each EPG. So EPG-A will need a relationship with EPG-B. EPG-B, the middleman, will need a relationship with EPG-C. Now these relationships is what's known as contracts. So imagine EPG-A was a user and EPG-B was web. How usually does a user need to connect to the web? Well, port 80 is the HTTP port, is the TCP port for HTTP, and 443 is the TCP port for HTTPS. So for example, as part of a contract between EPG-A and EPG-B, we would have to allow for those two ports to be open. So that's one very simplistic example, just so you get the concept. Obviously, within a contract, you could have multiple ports that require to be open, but this is just really to explain the concepts. So diving into the contract area, so contract being a definition of a policy, exactly how I defined it in the last slide, how an EPG communicates with other EPGs. Now the subject is what's being discussed, and think of this as an access list, a named access list with many lines. So think of the contract as the named access list and the subject of the many lines within the named access list. Many ports you need to open for those types of purposes. And then a filter is kind of like a class map. What do you want to classify? Do you want to classify SNMP? Do you want to classify post office protocol? What do you want to classify? And then the action is kind of not too dissimilar to a policy map. What do you want to do with it? So the next slide talks about the actions you can perform. You can permit, deny, redirect, log, copy, and mark. Stuff we're kind of used to, hey? This slide is pretty much once again reiterating the fact that a contract contains multiple subjects, multiple lines, for example, in the access list. And this top bit is within the subject, you have the filter, what do you want to classify, the action, what do you want to do with it, and just a naming label there. So back to our user, web, app, and DB diagram, that how the most application guys think. This is a very generic terminology, but this doesn't necessarily, I think I said this in the first video, don't have to go by it, but this is kind of a generic one that, as probably some of you know, a lot of people use, and just makes it a bit easier obviously to explain this and apply it to the realms of our terminologies within ACI. So this is also showing that communication between user and web and user can be bidirectional. It's both ways. Think of an access list once again, applying it inbound or applying it outbound. Exactly the same here. This is explaining that this is explaining the consumer provider model. So users are a consumer of the web. Web are a consumer of application servers. Then the application servers provide to the web. Web servers provide this to the users. So in this case, a user is just a consumer. The app server is just a provider. The web farm is actually forming two of those functions as a provider and a consumer, so it can do both. So this is pretty much a classic example of our challenges in today's world. You need to make all the configuration required, how web servers are attached, application servers are attached, firewalls, load balances, IPSs, etc., etc. This is just a hundredth of the configuration we know. So in red, we've obviously got this server, the load balancer dependencies, and the firewall down here, etc., etc. So if you add a couple of web servers, you now need to update this configuration. Then you need to think about, how does this apply in the load balancing area? And then you've also got to think, how does this apply to the firewall side of things? And potentially different teams are responsible for these areas, and that's time consuming. Think of it also as Chinese whispers as well. Communication could be bad, things aren't done correctly. What would be much nicer is just have one application that can manage all this and automate it all in one. So there's not going to be any mistakes, and things are just going to be provisioned via a simple GUI, simpler GUI. So how do we do this in ACI? Let's add a couple more web servers. Something I haven't mentioned yet is if you've categorized your EPGs, say for example VLAN 10 EPG for users, now the users would have to go via a switch or something, whether it's virtual, whether it's bare metal users, doesn't matter. Have to go via a switch, and then if we're building this, we would actually have to be responsible for tagging it with the correct VLAN. Say for example VLAN 10, that would be our responsibility. Of course, it's also our responsibility to set up VLAN 10 for that particular EPG. But once that's done, I'm thinking of sort of the future, many more hosts being provisioned for this at a later date. Once that's been configured, which doesn't take long at all, as soon as a future client, as long as you configured it, is connected, it will attach to the leaf, whether it's direct or via another switch in between, doesn't matter. It will detect that it's tagged with VLAN 10. You're part of VLAN 10. I need to apply you to the endpoint group for users. So no static configuration is required there. So this is what we've got to do in ACI. Understand our network, understand our requirements from an application point of view. Once again, I know this is very generic, but just so you get the concept. Define your relevant EPGs. In this example, outside, web, app, and database. Define what VLANs are going to be in them. Define what VXLANs are going to be part of them. What existing layer 4 to 7 devices have you got? How many firewalls have you got? Do they need clustering? How many load balancers have you got? Same old questions. These need to obviously be integrated into the fabric as well. How are they going to relate and depend on the other endpoint groups? These are the contracts. What contracts are we going to define? Which EPGs are they going to be going between? So we'd need a contract which is web contract. So this web contract here would be between the outside EPG and the web EPG. So this contract, as I explained in the previous slide, we would need to open up port 18443. Something I haven't mentioned yet that's critical to mention. So as I mentioned before, a spine discovers a leaf and discovers the next leaf, leaf, then spine, then leaf, etc., in that fashion to discover the whole topology and create its own routing between all of them. So that does all the layer 1 to 3 for you. No layer 4 to 7 is obviously configured until you need to, for example here. Because that's the case, security is great. It's there's nothing is allowed through, so everywhere is an implicit deny by default, which is something that security guys would absolutely love. So you only need to sort of open as and when you need to. And what's really clean and beautiful about this is one day maybe this application will go away and something else will provision somewhere else. So what you can do is deprovision that, and that will take all the configuration away from the fabric. So not only is that much easier to manage and a lot cleaner and simpler, it's less likely mistakes would be made as well. I can't stop stressing it's a great solution here. Then going between web and app, for example, is this contract here would be between these two guys here. This contract here would be between these two guys here. So that's where your web servers talk to application servers. So obviously simplistically we only allow the Java port 8081 to go through, but obviously in a real environment quite a few more would have to be holes punched through, as I say. Then with the database contract between these guys here, that is an example of the port for SQL 1433. So EPG is defined, service node integration defined, contracts defined, and you can only fit so much into this page, but that would obviously be under the bridge domain, the VRF, etc., etc. But it's fairly intuitive hierarchy. You start with the top thing first, the customer, and then the VRF, etc., etc., etc. So now you have to tie it in together. The APIC obviously does all of this. This is my favourite movement in a second. There you go. So that's everything tied together. Can't explain it from an everything point of view, but I'm sure you get the concept. Define the things you need to define that I've explained, then link them all together. Then that's not only will that provide you the end-to-end network for the app on the application's behalf, but it will also apply the policies between them and what's allowed and what's not allowed. So now I'm on part 2 of this video, which is actually going to discuss the actual ACI fabric. So all routing between the leaves and the spines is based upon layer 3, and it's IP using VXLAN tagging actually. So everything here is using VXLAN. Obviously we want to use something that's incredibly scalable. As you know, VXLAN has the ability to have 16 million IDs, unique IDs there. So this is really fit for future proof here as well. So as I say, everything layer 3 between the spines and leaves. MPBGP is running, multi-protocol BGP, and all these spines will act as route reflectors to keep all the routing tables up to date with where the leaves are connected, etc., etc. Like I say, layer 3, all the routing, and just simply the routing is at the spines to really quickly route between the leaves, and all the intelligence like QoS, ACLs and SLAs and whatever you need is what you need to deploy on the leaves. So as I mentioned, let me explain this next. So VXLAN is an open standards protocol, but with a few fields we can adjust. So Cisco have done exactly that, and the format also has what's known as a virtual tunnel endpoint, or VTEP header as well. So this is what is very Lisp orientated. So if you haven't heard of Lisp, Lisp stands for Locator ID Separation Protocol. Really kind of like designed for mobility, should VMs move around from place to place. So what it does, there's two portions to an address now. There's what's known as the locator, and in this case the locator will be what's known as a VTEP address. Okay, so they're individual for each leaf. And then there'll be the endpoint. So as soon as an endpoint moves to another guy, the locator portion of the address will change, which greatly means that the endpoint address, IP address, which we wouldn't want to change, doesn't have to change, which once again saves a lot of manual intervention. But there'll be a unique ID, VTEP ID for each of these guys as well. And if you know how Lisp works, also what's really cool about this is if it's going via if it's moved to a new leaf, it will have a new VTEP locator number. It won't be like a simple case of routing via the old one to get to the new one. No trombone routing. Everything's really nicely sort of updated in accordance with that, which is pretty cool. So, and yeah, also with Lisp, as you know, there's a mapping server, a mapping resolver, which is automatically provided as part of the fabric, which will perform all these functions and do all the updating as required. Now, I mentioned that you can have all the different types of encapsulation, so VXLAN here, VLAN here, NVGRE here, whatever it is. Obviously the VXLAN encapsulation between here and here is different. This is where you have the extra VTEP header. So even if you had a VXLAN going from here to here, it would change. Now when you got a packet that's going now entering the spine from the egress of the leaf, this is where a process known as normalization will occur. So regardless of whatever the format of these are all different, they will convert to the Cisco's VXLAN tagging that I've just explained, and that process is what's known as normalization. So the packet will be rewritten basically. The payload there, and you know, we're familiar with this side of things pretty much. Oh, let me go back. This is the VTEP header here, and IP, NVGRE, outer IP, etc., etc. So this slide is pretty much talking about what I've just mentioned, actually, the Lisp equivalent encapsulation. So if this VM moves from here to there, the VTEP address will change. Nothing else really needs to change. So this slide is pretty much talking about convergence. So obviously Lisp has got to make updates to the routing table should things move away. However, from a convergence point of view, so it's really minimal, and you know, we're kind of in the realms of microseconds here, if not less. If the VM here moves to leaf 5, what it will do is when it gets to leaf 5, it will send a gratuitous up back to leaf 2, so that whilst communication is still happening from this VM to the VM thinking it should still be on leaf 2, what it will do is it will actually install a bounce entry, which drastically reduces convergence time to get to the final leaf, which is really cool. And then obviously once the routing table has all been sort of updated, this will obviously take the more optimal path to get to where it needs to go. So I mentioned earlier that with if you've got a new bare metal server that you've plugged into a leaf, if you've got a VM server that you've plugged into a leaf, if you've got a router, whatever plugs, if it plugs directly, if it plugs indirectly by another switch, and you've just configured the EPG to cope with the sort of outside portion in that way, doesn't matter. When you've got that connection to the leaf, how is the policy going to be applied? When it attaches to the fabric the APIC will discover that it's been attached. If you've tagged it with the relevant VLAN, it will then know which EPG to place it into. Then this slide talks more about EPG to EPG communication now. So if we talk here about a user wanting to access the web, okay, that's EPG to EPG communication. Doesn't matter. It could be connected to the same leaf. Doesn't necessarily have to be. If you've attached a web server and you wanted to get it to talk to one of the app servers, which happens to be in this case on another leaf, that's irrelevant. All I'm trying to really explain here is just EPG to EPG communication. So that's one perspective. And then this type of EPG communication to an app is another one. So this is just talking about one-to-one EPG communication via a contract. So part one, the first one here is pretty much what the last slide covered. And then we're going to find out how we're going to get to the destination EPG now. It's just routing based in this respect. If the destination endpoint group is known, the policy will be enforced and then the policy applied bits are marked. If, however, the destination EPG is not known, the packet from the leaf will be sent to the spine to query what the address is for the other leaf that the other endpoint is attached to. If it can't find it, drops it. If it does find it, then the policy bit is enforced as the destination endpoint group is now known. So this is the day in the life of a packet. So we've got a packet here sourced from a VM, attached to an ingress port group. The vSwitch happens to tag it with the VLAN you want to use for whatever you set the endpoint group for that endpoint group you want it to be in. The vSwitch will then encapsulate it with a relevant header as well. This is where normalization occurs. The leaf swaps the ingress encapsulation with the VXLAN we've done and perform the functions. And then if it knows how to get to the end leaf, the spine will simply switch it to here. If it doesn't know, what the leaf will do is send an anycast to all the spines, and then one of the spines will respond to the sending leaf on the destination leaf's behalf. Then it'll get to the destination leaf, and then it will swap the VXLAN header from here to whatever the header needs to be down here. Forward it to the vSwitch and to the endpoint. Everyone's happy. What you may be familiar with port channeling, VPCs, fabric path, etc., etc. Load balancing is done on a per flow basis. So if you have one IP here going to another IP here, as it's only a one-to-one mapping, before we were only familiar with it's only possible to go via one path and it will only ever go on that path. The only way you can have multiple links used is to have multiple IPs, or however you call it, multiple ports, however you do your hashing. Now what is possible, even on a one-to-one basis with ACI, is the concept of FLOWLET switching. So a FLOWLET is a combination of packets, so it's a few packets lumped together, and what that allows you to do is that even on a one-to-one basis the FLOWLETs can go via alternate paths. If you see here, these will go a different way now. If you see here, very cool. Each leaf has a timestamp for each FLOWLET, so when they are received on ingress at the destination leaf, they'll be put back into the correct sequence. Another real cool concept is atomic counters. So these are pretty much applied to the leaves, and this allows real granular measurement, telemetry sort of level management for bytes, bits, packets, flowlets, you name it, anything like that. Latency, it can measure sort of any loss, and whatever you want it to measure, it has the capability of doing that. So if, for example, we have a VM attached to leaf 2 attached to a VM on leaf 5, there's 4 spines. So as we're using FLOWLET switching, there's 4 multiple paths that can be taken from VM2 to VM5. And what it will do is actually be able to measure the amount of packets for each path that was at the egress of, for example, leaf 2. And it will be able to compare this with, for each path, the ingress of path, or the 4 paths for the destination being leaf 5. So usually the case will be ideally 0, but there was a difference of 2 and minus 3 here. This is what will determine your health score. So like I said, real powerful measuring tool for, for the leaves, and it's really useful for troubleshooting as well. So there's all sorts of troubleshooting views. You can look on the ACI GUI. It can do like pings, trace routes between each leaves, each spine, and give you all the relevant information. Really dive down deep. We'll talk about where the CPU measurements, memory measurements, bandwidth per port measurements, latencies, health scores, packet loss, jitter, anything like that. We'll be able to get measurements for on the whole ACI fabric. Pretty cool. So I hope you've enjoyed these 2 series of videos. As I mentioned, there are many videos on the CPOC YouTube channel, service provider based, data center based. We've got a lot more to come. It's really exciting. This is the link for our YouTube channel, and yes, please like this video. Thank you.